So today we're going through literally everything about trigonometry, the entire history, how the math actually works from the ground up, why it matters, and where it's headed in the future. This is going to be a journey, so get comfortable and let's go back to where this all started. We're talking about the second millennium BC. That's like 2,000 years before Jesus was even born. The Egyptians had this document called the Rhine Mathematical Papyrus, copied by a scribe named Ames around 1650 BC, and buried in this papyrus are these problems about pyramids. Here's the deal with ancient Egypt. They're building these enormous pyramids, right? And when you're building a pyramid, you need every face to have the same slope. You can't have one side steeper than another or the whole thing looks ridiculous. So they came up with this measurement called the secant. The secant was basically the ratio of the horizontal distance to the vertical height. If you know modern trig, you're thinking, wait, that's the cotangent. And you'd be right. But the Egyptians didn't think of it as a trigonometric ratio. To them, it was just a length, just a practical measurement for construction. Meanwhile, over in Mesopotamia, the Babylonians were doing their own thing with triangles. These people were obsessed with astronomy and keeping track of celestial movements. They had divided the circle into 360 degrees. And by the way, we still use that system today because of them. Their number system was base 60, which is why we have 60 minutes in an hour and 60 seconds in a minute. When you check the time on your phone, you're using Babylonian mathematics. The Babylonians also had this clay tablet called Plimpton 322, which dates back to around 1800 BC. This tablet is absolutely wild. It contains 15 rows of what we now call Pythagorean triples. These are sets of 3 whole numbers, where the square of one plus the square of another equals the square of the third, like 3, 4, 5, or 5, 12, 13. The tablet has these calculated with incredible precision, and historians still argue about exactly how they did it and what they used it for. But the point is, these ancient civilizations understood that there were special relationships between the sides of triangles. Now, fast forward to around 300 BC. The Greeks entered the picture, and this is where trigonometry starts becoming systematic. Before the Greeks, people were using these ideas practically, building stuff, measuring stuff. But the Greeks wanted to understand the theory behind it all. The big innovation from the Greeks was the concept of the chord. Imagine you've got a circle and you draw a line that cuts across it. That line is a chord. The Greeks realized that the length of a chord depends entirely on the angle it makes at the center of the circle. And if you know the angle, you can calculate the length of the chord. This became the foundation of Greek trigonometry. The person who really kicked this off was Hipparchus of Nicaea, who lived from around 180 to 125 BC. Hipparchus is called the father of trigonometry, and for good reason. He created the first known trigonometric table, a table of chord lengths for different angles. This was revolutionary. Suddenly, if you knew an angle, you could look it up in a table and immediately know the corresponding chord length. No complicated calculations needed in the moment. Hipparchus was doing this for astronomy. The Greeks were obsessed with understanding the movements of the sun, moon, and planets. They wanted to predict eclipses, track the seasons, figure out the paths of celestial objects. And to do all of that, you need trigonometry. You need to be able to calculate distances and angles in space. Then comes Claudius Ptolemy around 140 AD. Ptolemy took everything Hipparchus had done and expanded it massively. He wrote this astronomical treatise called the Almagest, and in it he included incredibly detailed trigonometric tables. These tables were so comprehensive and so accurate that they were used for over 1,000 years. Think about that. For more than a millennium, if you needed to do trigonometry, you were using Ptolemy's work. Ptolemy's approach was still based on chords, like Hipparchus. But here's the thing about chords. A chord is related to sine. Specifically, half of a chord is the sine of half the angle. So the Greeks were actually dealing with what would become our sine function. They just didn't think of it that way yet. This is where things get really interesting, because the Indians completely transformed trigonometry. We're jumping to around 400 to 500 AD, during something called the Gupta period. This is when Indian mathematics and astronomy were flourishing. The Indians made a huge conceptual leap. Instead of using chords like the Greeks, they started using what they called the ja, which is basically the sine function as we know it today. The difference is subtle but important. With a chord, you're measuring a line that crosses a circle. With the sine, you're measuring half of that, which corresponds directly to the vertical height in a right triangle. There was this collection of astronomical texts called the Siddhantas. There were 5 of them, and the most important was called the Surya Siddhanta. These texts described not just sine, but also cosine, versine, and even the inverse sine. This was centuries before Europe would see these ideas. Then there's this guy, Aryabhata, who lived from 476 to 550 AD. Aryabhata wrote this work called the Aryabhatiya, and it's one of the most important mathematical texts ever written. He created sine tables that were way more detailed than anything the Greeks had produced. The Indians divided the 90-degree arc into 24 sections, so they had sine values for every 3.75 degrees. And here's what's cool. The Indians weren't just copying Greek astronomy. They had their own methods, their own approaches. They were doing serious calculations about the movements of planets, the timing of eclipses, all of this stuff. Indian astronomy was incredibly sophisticated. The concept of sine was so useful that it spread. It went from India to the Islamic world, where it was translated and further developed. Eventually, it made its way to medieval Europe through these translations. Now we get to the Islamic Golden Age, which ran from roughly the 8th century to the 14th century. This is when trigonometry became its own independent branch of mathematics, separate from astronomy. Around 770 AD, Indian astronomical texts reached Baghdad. The Caliph al-Mansur had scholars translating these works into Arabic. One of these translated texts was called the Zij al-Sindin, which introduced Indian calculation methods to the Islamic world. Enter al-Khwarizmi. You might know this name because the word algorithm comes from it. Al-Khwarizmi lived around 780 to 850 AD, and he did a ton of work on trigonometry. He produced improved versions of the Sai al-Sinhind, and he developed procedures for working with tangents and cotangents to solve astronomical problems. He made sine and versine tables. His work was copied and used for centuries. Then around 860 AD, there's Habash al-Hasib al-Marwazi, who created the first table of cotangents. And later, in the 10th century, there's Abu al-Wafa, who made even more advances. These Islamic mathematicians knew all 6 trigonometric functions: sine, cosine, tangent, cotangent, secant, and cosecant. They weren't just using these for astronomy anymore. They were using them for geography, for surveying, for architectural calculations. The Islamic world also developed spherical trigonometry to an incredibly high level. Spherical trigonometry is about triangles drawn on the surface of a sphere instead of on a flat plane. This is crucial for navigation and astronomy because the Earth is round and the celestial sphere is, well, a sphere. There's this mathematician Nasir al-Din Tusi in the 13th century who basically systematized spherical trigonometry. He wrote a treatise called Treatise on the Quadrilateral, where he listed 6 different cases of right-angled triangles in spherical trigonometry. He and another mathematician named Bhaskara are probably the first people to treat trigonometry as its own independent mathematical discipline, separate from astronomy. The Islamic scholars also proved the law of sines for spherical triangles. The law of sines is this relationship between the sides and angles of a triangle, and having it for spherical triangles was a massive breakthrough for navigation. When these Islamic texts started getting translated into Latin and reaching medieval Europe, European mathematicians suddenly had access to all of this knowledge. We're talking about the 12th and 13th centuries now. One of the big figures here is Regiomontanus, who lived from 1436 to 1476. He wrote this book called The Triangulis Omnimodis, on triangles of all kinds, which he finished in 1464, though it wasn't published until 1533. This book basically introduced European scholars to systematic trigonometry. It covered both plane trigonometry and spherical trigonometry, and it became hugely influential. Then, in 1595, a German mathematician named Bartholomeus Pitiscus published a work on trigonometry that might have actually coined the word trigonometry itself. The word comes from Greek trigonon, meaning triangle, and metron, meaning measure. So trigonometry literally means measuring triangles. The 17th century is when things really took off in Europe. In 1583, a Danish mathematician named Thomas Finke introduced the terms tangent and secant. Before this, these functions had different names or were described in more roundabout ways. Then, in the early 17th century, a French mathematician named Albert Girard was the first to publish the abbreviations we still use today: sin for sine, cos for cosine, tan for tangent. These abbreviations became standard, but the biggest development of the 17th century was when mathematicians started connecting trigonometry to calculus and complex numbers. In 1682, Gottfried Leibniz proved something remarkable. He proved that sine isn't an algebraic function. Even though sine looks like it might be a ratio of sides, which would make it a rational function, it's actually what's called a transcendental function. It can be expressed as a finite algebraic formula. This was a huge theoretical breakthrough. Now we get to Leonhard Euler, and this is where trigonometry becomes truly modern. Euler lived from 1707 to 1783, and he was probably the most prolific mathematician who ever lived. He contributed to basically every area of mathematics. In 1748, Euler published Introduction to the Analysis of the Infinite, and in this book he did something incredible. He showed that sine and cosine functions are actually alternating series formed from the exponential function. He connected trigonometry to exponential functions through what we now call Euler's formula. Euler's formula is e to the I x equals cosine x plus I sine x. Let's break this down because it's genuinely one of the most beautiful equations in all of mathematics. On the left side, you've got E, which is Euler's number, about 2.718. This is the base of natural logarithms, and it shows up everywhere in mathematics and nature: compound interest, population growth, decay processes, probability. Then you're raising it to the power of I times x, where I is the imaginary unit, the square root of -1. On the right side, you've got cosine x plus I sine x. These are our trigonometric functions, but now they're connected to this exponential expression through the imaginary unit. This formula tells us that trigonometric functions and exponential functions are deeply related through complex numbers. It's not just a mathematical curiosity. This connection is used constantly in engineering, physics, signal processing, quantum mechanics. When physicists describe waves or oscillations, they often use complex exponentials because they're easier to manipulate than sines and cosines. And there's a special case of Euler's formula that's even more mind-blowing. If you set x equal to pi, you get e to the I pi equals -1. Or, rearranging it, e to the I pi plus 1 equals 0. This is called Euler's identity, and it connects 5 of the most important numbers in mathematics, e, I, p, 1, and 0, in one simple equation. The physicist Richard Feynman called it the most remarkable formula in mathematics. Okay, so we've covered the history. Now let's get into how trigonometry actually works. We're going back to basics, but I promise this is going to make sense. Start with a right triangle. A right triangle is a triangle where one of the angles is 90 degrees. A right angle. The side opposite the right angle is called the hypotenuse. It's the longest side of the triangle. Then you've got two other sides. Depending on which of the other angles you're looking at, one side is adjacent to that angle and one side is opposite to it. Now, here's the key insight that makes trigonometry work. If you take a right triangle and you know one of the non-right angles, the ratios between the sides are always the same, no matter how big or small the triangle is. Let me say that again because it's crucial. The ratios are constant for a given angle. So if you have a 30-degree angle in a right triangle, the ratio of the opposite side to the hypotenuse is always the same value, whether your triangle is tiny or huge. That ratio is about 0.5, and we give this ratio a name. We call it the sine of 30 degrees. The sine of an angle is the ratio of the opposite side to the hypotenuse. The cosine of an angle is the ratio of the adjacent side to the hypotenuse. The tangent of an angle is the ratio of the opposite side to the adjacent side. People remember these with the mnemonic SOHCAHTOA. So, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. To, tangent is opposite over adjacent. So if you know an angle and you know one side of the triangle, you can use these ratios to find the other sides. Or if you know two sides, you can find the angle. This is incredibly powerful. Let's do a concrete example. Say you're standing some distance away from a building and you want to know how tall the building is. You can measure your distance from the building. That's easy. Just walk it off. Let's say you're 90 feet away. Now you look up at the top of the building and measure the angle. Let's say it's 35 degrees. That's your angle of elevation. Now you've got a right triangle. The ground distance is 90 feet. That's adjacent to your angle. The height of the building is opposite your angle. You want to find that opposite side. So you use tangent, because tangent is opposite over adjacent. Tangent of 35 degrees equals height divided by 90 feet. You look up the tangent of 35 degrees. It's about 0.7. So 0.7 equals height divided by 90. Multiply both sides by 90, and you get the height is about 63 feet. That's the building's height, and you figured it out without climbing it or even getting close to it. This is why trigonometry is so useful. It lets you figure out distances and heights without direct measurement. Ancient astronomers used it to calculate distances to the moon and planets. Surveyors use it to map land. Architects use it to design buildings. Now, the triangle approach is great, but there's another way to think about trigonometry that's even more powerful. It's called the unit circle. A unit circle is a circle with a radius of 1, centered at the origin of a coordinate system. So it's a circle where every point on the edge is exactly 1 unit away from the center. Imagine you're at the center of this circle, and you draw a line from the center to some point on the edge of the circle. That line makes an angle with the positive x-axis. We measure this angle counterclockwise from the right side of the circle. So 0 degrees is pointing right, 90 degrees is pointing up, 180 degrees is pointing left, and 270 degrees is pointing down. Now here's where it gets cool. Take the point where your line hits the circle. That point has an x-coordinate and a y-coordinate. The x-coordinate is the cosine of your angle. The y-coordinate is the sine of your angle. Why? Well, think about it. If you drop a perpendicular line from your point down to the x-axis, you've created a right triangle. The hypotenuse is the radius of the circle, which is 1. The adjacent side is the x-coordinate. The opposite side is the y-coordinate. So cosine of the angle equals adjacent over hypotenuse, which is x coordinate over 1, which is just the x coordinate, and sine equals opposite over hypotenuse, which is y coordinate over 1, which is just the y coordinate. This means every point on the unit circle corresponds to an angle, and the coordinates of that point tell you the sine and cosine of that angle. It's a visual, geometric way to understand these functions. And this extends beyond right triangles. With a right triangle, you can only have angles between 0 and 90 degrees. But on the unit circle, you can keep going around. You can have angles bigger than 90 degrees. You can go past 180 degrees, past 270 degrees, past 360 degrees, and just keep going. The sine and cosine values just keep cycling through the same pattern over and over. They're periodic functions. This is why sine and cosine are so useful for describing anything that repeats or oscillates. Sound waves, light waves, alternating current, the motion of a pendulum, planetary orbits, anything that cycles can be described using sine and cosine. Quick detour here because we need to talk about radians. You're probably used to measuring angles in degrees. A full circle is 360 degrees. A right angle is 90 degrees. This comes from the Babylonians and their base 60 number system. But there's another way to measure angles called radians, and it's actually more natural mathematically. Instead of dividing a circle into 360 arbitrary pieces, we measure angles based on the radius of the circle. Here's how it works. Take the radius of a circle and wrap it around the circumference. The angle you've swept out is 1 radian. Keep wrapping the radius around the circle. The full circle has a circumference of 2 pi times the radius. So, if you keep wrapping, you'll go around the circle exactly 2 pi times. That means a full circle is 2 pi radians. So 2 pi radians equals 360 degrees. That means pi radians is 180 degrees. Half of pi radians is 90 degrees, and so on. Why use radians instead of degrees? Because radians make calculus work beautifully. When you take the derivative of sine, if you're using radians, the derivative of sine x is just cosine x, clean and simple. If you are using degrees, you'd get some messy constant factor in there. Radians keep everything clean. Plus, radians connect the circular and exponential functions through Euler's formula. When you write e to the I theta equals cosine theta plus I sine theta, that theta is measured in radians. In math and physics and engineering, radians are the standard. Degrees are mostly used for practical applications where they're easier to visualize. Now, let's talk about identities. Trigonometric identities are equations involving trig functions that are true for all angle values. They're like the rules of the game. If you know these identities, you can manipulate complicated trig expressions and simplify them. The most basic identity is the Pythagorean identity. Remember the Pythagorean theorem for right triangles. The square of one side plus the square of another side equals the square of the hypotenuse. If you apply this to the unit circle, you get sine squared theta plus cosine squared theta equals 1. This is true for any angle theta. Why? Because on the unit circle, the radius is 1. The x-coordinate is cosine theta. The y-coordinate is sine theta. If you apply the Pythagorean theorem to the triangle formed, you get cosine squared plus sine squared equals 1 squared, which is 1. This identity is used constantly to convert between sine and cosine, to simplify expressions, to solve equations. You can rearrange it to say cosine squared equals 1 minus sine squared, or sine squared equals 1 minus cosine squared. Then there are angle sum formulas. These tell you how to find the sine or cosine of a sum or difference of angles. For example, sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta, and cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. These formulas look complicated, but they're incredibly useful. They let you break down complex angles into simpler pieces that you can calculate. There are double angle formulas too. Sine of 2 theta equals 2 sine theta cosine theta. Cosine of 2 theta equals cosine squared theta minus sine squared theta, which you can also write as 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. And there are half angle formulas, product to sum formulas, sum to product formulas. The list goes on. Trigonometry has more identities than probably any other area of basic math, and mathematicians have proven all of them rigorously. They're not just approximations or rules of thumb. They're exact relationships that always hold. Everything we've talked about so far works for right triangles and the unit circle. But what if your triangle doesn't have a right angle? What if you've got an oblique triangle where all 3 angles are different? This is where the law of sines and the law of cosines come in. These are generalizations of trigonometry that work for any triangle. The law of sines says that in any triangle, the ratio of a side length to the sine of its opposite angle is the same for all 3 sides. So A over sine A equals B over sine B equals C over sine C, where A, B, C are the side lengths and A, B, C are the opposite angles. This law is super useful when you know 2 angles and 1 side, or 2 sides and an angle opposite one of them. You can solve for the unknown parts of the triangle. The law of cosines is a generalization of the Pythagorean theorem. It says that c squared equals a squared plus b squared minus 2ab cosine c, where c is the side opposite angle c. Notice that if c is 90 degrees, cosine of 90 is 0, and this reduces to just c squared equals a squared plus b squared. That's the Pythagorean theorem. The law of cosines works for any triangle, right or oblique. With these 2 laws, you can solve any triangle if you know enough information. You need at least 3 pieces of information, like 2 sides and an angle, or 3 sides, or 2 angles and a side. Given that, you can find everything else. Let's get into something that might seem simple, but is actually really interesting. How do we actually calculate specific values of sine and cosine? Like, why is the sine of 30 degrees equal to 1/2? Why is the cosine of 60 degrees also 1/2? These aren't random numbers. Start with an equilateral triangle. All 3 sides are the same length and all 3 angles are 60 degrees. Now, split this triangle down the middle with a vertical line from one vertex to the opposite side. You've created two right triangles. Each right triangle has angles of 30, 60, and 90 degrees. If the original equilateral triangle had sides of length 2, then when you split it, the hypotenuse of your right triangle is 2 and the base is 1. The height you can figure out using the Pythagorean theorem. 1 squared plus height squared equals 2 squared. So height squared equals 3, which means the height is the square root of 3. Now look at the 30-degree angle. The opposite side is 1, the hypotenuse is 2. So sine of 30 equals 1 over 2, which is 0.5. The adjacent side is root 3. So cosine of 30 equals root 3 over 2, which is about 0.866. Look at the 60-degree angle. The opposite side is root 3. The hypotenuse is 2. So sine of 60 equals root 3 over 2. The adjacent side is 1. So cosine of 60 equals 1/2. Notice that sine of 30 equals cosine of 60, and cosine of 30 equals sine of 60. This isn't a coincidence. Sine and cosine are complementary functions. The sine of an angle equals the cosine of 90 minus that angle. This is where the name cosine comes from. It's the complement sign. Now try 45 degrees. Take a right triangle where the two non-hypotenuse sides are equal. Each of the non-right angles must be 45 degrees. If each leg has length 1, the hypotenuse has length root 2 by the Pythagorean theorem. So, sine of 45 equals 1 over root 2, and cosine of 45 also equals 1 over root 2. They're the same because the triangle is symmetric. 1 over root 2 is about 0.707. Often this is written as root 2 over 2 by rationalizing the denominator. These special values, 30, 45, 60 degrees, come up constantly. They're the angles you can construct with a compass and straight edge. They're the angles that have nice closed form expressions, and they're the ones you're usually expected to memorize. But what about other angles? Like, what's the sine of 23 degrees? Well, you'd use a calculator or a table, but those values don't have nice, simple forms. They're what we call transcendental numbers. They can't be expressed exactly as a ratio of integers or even as a solution to a polynomial equation. You can only approximate them. Actually, there's a whole theory about which angles have exact algebraic expressions for their sine and cosine values. It connects to something called Galois theory in abstract algebra. The angles that work are related to constructible polygons. You can construct a regular pentagon with compass and straight edge, so you can find exact expressions for sine and cosine of 36 degrees and 72 degrees. But you can't construct a regular heptagon, a 7-sided polygon, so sine and cosine of angles like 51.4287 degrees don't have nice algebraic forms. This might seem like abstract mathematical trivia, but it's actually connected to deep questions about what numbers are computable and what mathematical operations are possible. I want to spend a bit more time on the Fourier transform because it's one of the most important applications of trigonometry, and a lot of people don't really understand what it does. Joseph Fourier was a French mathematician in the late 18th and early 19th centuries. He was studying heat flow, and he made this incredible discovery. He found that any periodic function, any function that repeats over and over, can be represented as a sum of sine and cosine functions at different frequencies. This might not sound that impressive until you realize what it means. Take any complex waveform. Could be a sound, could be a radio signal, could be anything that varies with time or space. According to Fourier, you can break it down into a collection of simple sine waves. Each sine wave has a specific frequency and amplitude. Add them all together and you reconstruct the original signal. The Fourier transform is the mathematical operation that does this decomposition. You input a signal in the time domain, how it varies over time. The Fourier transform outputs the frequency domain, which frequencies are present and how strong each one is. This is unbelievably useful. When you compress an audio file to MP3, the algorithm uses a Fourier transform to figure out which frequencies are in the sound. It then throws away frequencies that humans can't hear well, keeping the ones that matter. That's how it makes the file smaller without making it sound terrible. When you tune a radio to a particular station, the radio is doing a kind of Fourier transform. All these radio signals are in the air at different frequencies. The tuner picks out just the frequency you want and ignores the rest. In image processing, you can take a Fourier transform of an image. This tells you what spatial frequencies are present, basically, where you have rapid changes versus smooth gradients. JPEG compression uses this. It transforms the image to the frequency domain, throws away high frequency details your eye can't see easily, and keeps the low frequency structure. That's how it shrinks file sizes. Quantum mechanics uses Fourier transforms to convert between position space and momentum space. These are two complementary ways of describing a quantum particle, and they're related by a Fourier transform. And here's the kicker. There's a version of the Fourier transform that works with non-periodic functions too. It's called the Fourier integral or continuous Fourier transform. This means you can decompose literally any function into sine and cosine components. Any signal can be thought of as made up of pure tones at various frequencies. This principle that complex things can be built from simple sinusoidal pieces is one of the most profound insights in all of mathematics, and it comes directly from trigonometry. Sound is a pressure wave traveling through air. When something vibrates, a guitar string, a vocal cord, a speaker cone, it creates compressions and rarefactions in the air that propagate outward. These pressure variations are sinusoidal for pure tones. A pure tone is a single frequency. If you plot the pressure as a function of time, you get a sine wave. The frequency determines the pitch. 440 cycles per second is the A above middle C on a piano. 880 cycles per second is the A 1 octave higher. The relationship is exponential. Each octave doubles the frequency. But real musical instruments don't produce pure tones. When you pluck a guitar string, it vibrates at its natural frequency, the fundamental, but it also vibrates at multiples of that frequency, the harmonics or overtones. The second harmonic is twice the frequency, the third is 3 times, and so on. Each harmonic is a sine wave. The actual sound is the sum of all these sine waves. Different instruments have different amounts of each harmonic, which is why a guitar sounds different from a piano playing the same note. The spectrum, the mix of harmonics, is the instrument's timbre or tone color. Fourier analysis lets us decompose any periodic sound into its harmonic components. You can take a recording of a musical note, do a Fourier transform, and see exactly which frequencies are present and how strong each one is. This is displayed in a spectrum analyzer, which shows frequency on the horizontal axis and amplitude on the vertical axis. When you digitally synthesize sound, you can build up any tone by adding sine waves. Early synthesizers literally did this. They had oscillators that produced sine waves at different frequencies, and you'd mix them together to create different sounds. This is called additive synthesis. There's also subtractive synthesis, where you start with a complex waveform like a sawtooth wave that has lots of harmonics, and then use filters to remove certain frequencies. A low-pass filter removes high frequencies. A high-pass filter removes low frequencies. A bandpass filter keeps frequencies in a certain range. Designing these filters involves trig. They're typically implemented as recursive equations with coefficients derived from sine and cosine. Modern music production uses tons of digital signal processing. Reverb effects simulate the sound of different spaces by adding delayed and filtered copies of the sound. The delays correspond to sound bouncing off walls. Short delays create early reflections. Longer delays with frequency-dependent absorption create the reverb tail. All of this processing involves convolution, which can be computed efficiently using FFT. Pitch shifting changes the frequency of a sound without changing its speed. This is tricky because you can't just speed up or slow down the audio. That would change both pitch and tempo. One method is to use the phase vocoder, which represents the audio in the frequency domain using a short-time Fourier transform. You can then manipulate the frequencies and phases before transforming back to the time domain. This relies heavily on trig. The physics of musical instruments involves lots of trig too. A vibrating string has a wave equation solution that's a standing wave, a sine wave with nodes at the ends. The normal modes are sine waves with different numbers of half wavelengths fitting on the string. The frequency of each mode is proportional to the number of half wavelengths. Wind instruments work similarly, but with air columns. Open tubes have antinodes at both ends. Closed tubes have a node at one end and an antinode at the other. The resonant frequencies depend on the length of the tube and whether it's open or closed. All of this is described with sine and cosine. Let's talk about wave interference, because it's one of the coolest phenomena in physics, and it's all about adding sinusoids. When two waves meet, they add together. If you've got one wave that's sine of x and another that's also sine of x, both with the same frequency and in phase, they add to give 2 times sine of x. The amplitude doubles. This is called constructive interference. But if one wave is sine of x and the other is negative sine of x, meaning they're 180 degrees out of phase, they cancel each other out completely. 0. This is destructive interference. More generally, if you add two sinusoids of the same frequency, but with different phases, you get another sinusoid of that same frequency. The amplitude and phase of the result depend on the original amplitudes and phases. There's a formula for this involving the law of cosines in vector form. If the frequencies are slightly different, something cool happens. You get beats. The two waves alternately reinforce and cancel, creating a pulsing pattern. The beat frequency is the difference of the two frequencies. This is why a piano tuner can tell if two strings are in tune. If they're slightly off, you hear beats, a wah 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 oscillation in the volume. When the beats disappear, the strings are perfectly in tune, oscillating at exactly the same frequency. Wave interference is crucial in optics. When light passes through two narrow slits, the light from each slit spreads out and the two patterns interfere. Where the waves are in phase, you get bright bands. Where they're out of phase, you get dark bands. This creates an interference pattern of alternating bright and dark stripes. This is called the double slit experiment, and it's one of the foundational experiments of quantum mechanics, showing that light behaves as a wave. Sound waves interfere too. Noise-canceling headphones work by generating sound waves that are 180 degrees out of phase with ambient noise. The waves destructively interfere and cancel out. You hear silence even though there's sound all around you. Radio signals interfere. If two radio stations broadcast on frequencies that are too close, their signals interfere and you get static or weird beating patterns. That's why radio frequencies are carefully regulated to avoid interference. In all these cases, understanding what happens requires adding sinusoids with different amplitudes, frequencies, and phases. It's trigonometry applied to real physical waves. In real-world situations, oscillations usually don't continue forever at constant amplitude. There's usually some friction or resistance that causes the oscillation to die down over time. This is called damping. A damped oscillation might look like sine of x times e to the negative kx, where k is a positive constant called the damping coefficient. The exponential decay factor causes the amplitude to decrease over time. The oscillation still has the same frequency, but it gets smaller and smaller. This kind of behavior shows up everywhere. A pendulum swinging in air gradually slows down due to air resistance. A plucked guitar string vibrates at its natural frequency, but the vibration decays over time. A mass bouncing on a spring gradually stops bouncing. All of these are damped oscillations. If you plot damped sine, you see the familiar sine wave, but with an envelope that's exponentially decaying. The wave stays between two exponential curves that get closer and closer to zero. Now, what if you drive an oscillating system? Meaning, what if you keep applying force to it? This gets really interesting. Imagine you've got a mass on a spring and you're pushing on it rhythmically. If you push at the right frequency, the natural frequency of the spring system, you get resonance. The amplitude of oscillation grows and grows. This is how you pump a swing. You push at just the right moment in the cycle, and the swing goes higher and higher. Resonance can be useful or dangerous. Musical instruments rely on resonance to amplify sound. A guitar string vibrates and causes the body of the guitar to resonate, making the sound louder. Radio receivers use resonance to tune into specific frequencies. The circuit is designed to resonate at the frequency of the station you want to listen to, but resonance can also destroy things. In 1940, the Tacoma Narrows Bridge collapsed because wind caused the bridge to oscillate at its resonant frequency. The amplitude got so large that the bridge literally tore itself apart. This is a famous example in engineering of why you need to understand resonance. The math of driven damped oscillations involves solving differential equations with trig functions. The solution has both a transient part that dies away and a steady state part that continues as long as you keep driving the system. The steady state solution is a sinusoid at the driving frequency, but with a phase shift that depends on how close you are to the resonant frequency. All of this is described using trigonometry combined with exponentials and complex numbers. It's a beautiful application that shows how these different areas of math work together. Let's talk about where trigonometry actually shows up in the real world, because it's everywhere, and I mean everywhere. Architecture and construction. When you're designing a building or a bridge, you need to calculate forces, angles, structural loads. Trigonometry is essential. If you're building a roof, you need to calculate the pitch. If you're building a suspension bridge, you need to figure out the tensions in all the cables. All of this requires trig. Navigation. Before GPS, sailors used celestial navigation. They'd measure the angles of stars above the horizon and use trigonometry to calculate their latitude and longitude. Even with GPS, the system still relies on trigonometry to triangulate your position from satellite signals. Astronomy. Obviously, this is what trigonometry was invented for. Astronomers use parallax, measuring how a star appears to shift position when viewed from different points in Earth's orbit, to calculate the distance to nearby stars. This is pure trigonometry, physics. Anytime you're dealing with forces at angles or projectile motion or waves, you need trig. When you throw a ball, its path is parabolic, and you can describe it using trigonometric functions. When you analyze a pendulum, the angle it makes can be described with sine or cosine. Music. Sound is a wave, right? And waves are sinusoidal. A pure tone is a sine wave at a particular frequency. Complex sounds are combinations of multiple sine waves at different frequencies, what we call harmonics. When you use a synthesizer to create electronic music, you're literally manipulating sine waves. Fourier analysis, which breaks down any complex wave into its sine and cosine components, is used all over audio engineering, computer graphics, and game development. When you rotate an object on screen, translate it, or apply perspective projection, you're using trigonometry. The 3D graphics in video games rely heavily on matrices that are built from sine and cosine values. Electrical engineering. AC circuits involve alternating current, which oscillates sinusoidally. Phase angles, impedance, resonance, all described with trig functions. Quantum mechanics. The wave functions that describe quantum particles are sinusoidal. Schrödinger's equation, which is the foundation of quantum mechanics, involves trigonometric and complex exponential solutions. Signal processing. This is huge. Anytime you're dealing with signals, audio, radio, digital communications, you use Fourier transforms. A Fourier transform takes a signal and breaks it down into its frequency components, all of which are sines and cosines. This is how MP3 compression works, how JPEG image compression works, how your phone talks to cell towers. Medical imaging, CT scans, and MRI machines use mathematical techniques based on Trig to reconstruct images of the inside of your body from sensor data, GPS, and location services. Your phone's GPS receiver picks up signals from multiple satellites, measures the time delays, and uses trigonometry to calculate exactly where you are on Earth. Animation and visual effects. Pixar and other animation studios use tons of trigonometry, character movements, camera angles, lighting calculations, especially ray tracing for photorealistic rendering, all involve Trig. Machine learning and AI. Neural networks used in image recognition often use something called convolutional neural networks, and the mathematics behind convolution involves lots of sine and cosine transforms. When AI processes images or audio, it's often working in the frequency domain, which means it's manipulating sines and cosines. Climate science. Weather modeling and climate simulations involve solving differential equations that describe fluid flow and heat transfer. The solutions to these equations involve trigonometric functions because the Earth is rotating and spherical. Robotics. When a robot arm moves, each joint rotates through a certain angle. To figure out where the end of the arm is in space based on all the joint angles, you need what's called forward kinematics, which is all about applying trig functions repeatedly. Inverse kinematics, figuring out what angles you need to reach a particular point, also uses trig extensively, and this is just scratching the surface. Trigonometry shows up in acoustics, optics, seismology, oceanography, crystallography, cryptography, economics, you name it. It's one of those areas of math that's genuinely universal. Let's talk more about how trig is used in video games, because this is a fun application that a lot of people interact with but don't think about. Every 3D video game is built on trigonometry. When you move your character, rotate the camera, or watch an object fly through the air, there's trig happening constantly in the background. Character animation. When a character walks, runs, or jumps, their limbs move in ways that can be approximated with trig functions. A simple walk cycle might have the leg angle varying as sine of time. More realistic motion uses inverse kinematics, where you specify where the hand should be, and the computer calculates what angles all the arm joints need to be at to reach that position. This is heavy trig. Skeletal animation works by representing characters as a hierarchy of bones. Each bone can rotate relative to its parent. The final position of a vertex on the character's skin depends on all the bones that influence it and their rotation angles. Computing this efficiently requires matrix math, and rotation matrices are built from sine and cosine. Physics simulation. Games simulate gravity, collisions, friction, all kinds of physical interactions. When something bounces, you need to calculate the angle of reflection. When something rolls down a slope, you need to break down forces into components parallel and perpendicular to the slope. When something orbits, its position follows an ellipse or circle described by trig functions. Projectile motion is a classic example. You shoot an arrow at some initial velocity and angle. The trajectory is parabolic. The horizontal component of velocity is v times cosine of the angle. The vertical component is v times sine of the angle. Using these, you can calculate where the arrow will be at any time. Many games have a day-night cycle. The position of the sun moves across the sky in an arc. This is often simulated using sine and cosine to vary the sun angle over the course of the game day. The lighting in the scene changes based on the sun position, which affects how everything looks. Procedural generation. Some games generate terrain, dungeons, or content algorithmically. Perlin noise and simplex noise, which are used to create natural-looking random terrain, use interpolation between random gradients at grid points. The interpolation function uses polynomial curves that can be related to trig functions. Shaders are little programs that run on the GPU to compute the color of each pixel. Shaders use trig functions all the time. You might use sine to create a wavy effect on water, or use cosine to compute how light reflects off a shiny surface based on the angle between the viewer, the surface, and the light source. Particle effects like fire, smoke, explosions use lots of small particles. Each particle might move in a slightly random direction. Selecting a random direction uniformly distributed in 3D space requires using trig. You generate random angles and convert them to a direction vector using sine and cosine. Camera control is another big area. In third-person games, the camera orbits around the character. The camera position is at some distance and angle from the character. When the player moves the analog stick, the camera angle changes, and you recalculate the camera position using trig. First-person cameras work similarly, but the camera is at the character's eyes. Audio positioning. In 3D games, sounds come from specific directions. To create realistic spatial audio, the game needs to figure out which direction each sound source is relative to the player and adjust the volume and stereo panning accordingly. This involves computing angles in 3D space. So what's the future of trigonometry? Is there still new stuff to discover? Or is it all figured out? Well, the basic theory of trigonometry is pretty well settled. We're not going to find a new trigonometric function or a new identity that nobody knew about. The core math has been solid for centuries, but the applications keep expanding. Every new technology seems to find new ways to use trig, quantum computing. Quantum computers work with qubits that exist in superpositions of states. The mathematics of quantum gates, the operations you can do on qubits, involves lots of rotations in high-dimensional complex spaces. These rotations are described using generalized trigonometric and exponential functions. When you think about a quantum bit, It's not just 0 or 1 like a classical bit. It's a superposition, a linear combination of 0 and 1 states. And this superposition can be represented as a point on the surface of a sphere called the Bloch sphere. Rotations of this sphere, which change the qubit state, are described using angles and trigonometric operations. Quantum gates, like the rotation gates, explicitly use trig functions. The Rx gate rotates a qubit around the x-axis by an angle theta, and its matrix representation involves cosine of theta over 2 and sine of theta over 2. The Ry and Rz gates work similarly for the other axes. When quantum algorithms manipulate qubits, they're chaining together these rotation operations. Machine learning and AI. Modern machine learning, especially deep learning, uses techniques like convolutional neural networks. Convolutions are mathematical operations that can be computed efficiently using Fourier transforms, which means they're ultimately based on trigonometry. There are neural networks called sinusoidal representation networks or siren networks that use sine as their activation function throughout. These have shown promise for tasks involving implicit neural representations, where you're trying to represent images, 3D shapes, or audio signals as continuous functions. The periodic nature of sine helps these networks learn high-frequency details better than traditional networks. Transformers, which are the architecture behind systems like GPT, use something called positional encoding. This encodes the position of words in a sequence using sine and cosine functions of different frequencies. The idea is that the periodic nature of trig functions helps the network understand position in a way that generalizes well gravitational wave detection. LIGO detected gravitational waves from merging black holes in 2015. This was a huge deal in physics. The signal processing required to pull these incredibly faint signals out of the noise involves sophisticated Fourier analysis. The gravitational waves themselves are oscillations in space-time. They cause the length of the LIGO arms to oscillate sinusoidally by an incredibly tiny amount, about 1/10,000th the diameter of a proton. Detecting this requires matched filtering, where you compare the noisy data to templates of what different types of gravitational wave signals should look like. As we build more gravitational wave detectors around the world and in space, the signal processing will only get more complex. We'll be detecting weaker signals, triangulating the direction they came from by comparing arrival times at different detectors, extracting information about the masses and spins of merging objects. Virtual and augmented reality. VR and AR headsets need to track the position and orientation of your head with incredible precision and very low latency. This involves lots of coordinates, transformations, and rotations, all of which use trig. Current VR headsets use a combination of accelerometers, gyroscopes, and external tracking systems. The data from these sensors has to be fused together in real time to figure out exactly where your head is and which direction you're looking. This involves quaternions, which are a generalization of complex numbers to 4 dimensions. Quaternions are great for representing rotations without the problems that plague other methods, and they're intimately connected to trigonometry. As VR and AR get more advanced, we're moving toward things like light field displays and holographic displays. These create truly 3D images by controlling the direction light travels, not just showing different flat images to each eye. The math behind these displays involves diffraction and wave optics, which again brings us back to sine and cosine autonomous vehicles. Self-driving cars use LiDAR and cameras to map their surroundings. Processing this sensor data involves lots of geometry and coordinate transforms. The car needs to figure out where obstacles are, how they're moving, what angles they're at relative to the car's heading. LiDAR works by shooting laser pulses and measuring how long they take to bounce back. The time delay tells you the distance, but you also need to know the angle the laser was pointing to figure out the 3D position of what you hit. The LiDAR sensor typically spins around, shooting lasers in all directions. Converting the raw time of flight and angle data into a 3D point cloud of the environment requires tons of trig calculations. Space exploration. As we send probes to Mars and beyond, and as we potentially establish bases on the Moon, navigation and communication become more complex. Trigonometry is essential for calculating trajectories, orbital mechanics, communication dish pointing angles. When you want to send a spacecraft to Mars, you can't just point it at where Mars is now and launch. Mars will have moved by the time you get there. You need to calculate the trajectory that will intercept Mars's orbit at the same time Mars is there. This is a complex optimization problem involving orbital mechanics, which is built on trig climate modeling. Climate models are getting more detailed and more accurate. They're incorporating finer spatial resolution, more complex atmospheric chemistry, better ocean models. All of these improvements involve solving partial differential equations numerically, and the solutions often involve trigonometric basis functions. When you simulate the atmosphere, you're solving equations for things like temperature, pressure, wind velocity, humidity. These variables vary in 3 dimensions and change with time. One common approach is to use spectral methods, where you represent the variables as sums of spherical harmonics. Spherical harmonics are like sine and cosine, but generalized to work on the surface of a sphere. Medical imaging keeps advancing too. New types of scans with higher resolution, faster imaging, better contrast. The reconstruction algorithms that turn raw sensor data into images use Fourier transforms and other techniques based on trig. CT scans work by taking X-ray images from many different angles around the patient. To reconstruct a 3D image of the interior, you use the radon transform and its inverse, which involves integrating over lines through the volume at different angles. MRI uses magnetic fields and radio waves to excite nuclear spins in the body. The signal you get back is a complex sinusoid whose frequency and phase encode spatial information. The raw MRI signal is in the frequency domain, and you reconstruct the image by doing a multidimensional inverse Fourier transform. Let's circle back to complex numbers, because the connection between trigonometry and complex numbers is genuinely deep and beautiful. A complex number is a number with a real part and an imaginary part. You can write it as a plus bi, where a and b are real numbers and I is the square root of -1. You can plot complex numbers on a plane, with the real part on the horizontal axis and the imaginary part on the vertical axis. Now, you can also represent complex numbers in polar form using their magnitude and angle. The magnitude is the distance from the origin. That's the square root of a squared plus b squared. The angle is measured counterclockwise from the positive real axis. That's the arctangent of b over a. And here's where trig comes in. You can write the complex number as r times the quantity cosine theta plus I sine theta, where r is the magnitude and theta is the angle. This is the polar form. But thanks to Euler's formula, you can write this even more simply as r times e to the I theta. The complex exponential e to the I theta is just a compact way of writing cosine theta plus I sine theta. This means multiplying complex numbers is easy in polar form. If you have r1 times e to the I theta 1 and r2 times e to the I theta 2, and you multiply them, you get r1 times r2 times e to the I times the quantity theta 1 plus theta 2. The magnitudes multiply and the angles add. This is way easier than multiplying out the a plus bi form. And this connection shows up everywhere in physics and engineering. Oscillating systems, electromagnetic waves, quantum wave functions. They're all described using complex exponentials, which are secretly just trig functions in disguise. When electrical engineers analyze AC circuits, they use something called phasors, which are complex numbers representing sinusoidal voltages and currents. The angle of the complex number is the phase angle of the wave, and the magnitude is the amplitude. Working with phasors is much easier than working with the actual time-varying sine and cosine functions. In quantum mechanics, the wave function is a complex-valued function. When you solve the Schrödinger equation, you get solutions that involve complex exponentials, which are connected to sine and cosine through Euler's formula. Before we wrap up, let's explore one more aspect of trigonometry that touches our daily lives in subtle ways: circular and rotational motion. Everything that spins or orbits involves trigonometry. The wheels on your car, the hard drive in your computer, the planets around the sun, the electrons around atoms. All of this is circular or near circular motion described by trig functions. When something moves in a circle at constant speed, its position can be described by x equals r cosine of omega t and y equals r sine of omega t, where r is the radius, omega is the angular velocity, and t is time. The velocity vector is perpendicular to the position vector, and the acceleration points toward the center. That's centripetal acceleration. This isn't just abstract physics. Your car's wheels rotate at different speeds, depending on how fast you're going. The transmission and differential use gear ratios to convert the engine's rotation to wheel rotation. When you turn, the inside wheels trace a smaller circle than the outside wheels, so they need to rotate at different speeds. The math of all this involves trig. In machinery, gears and pulleys transfer rotational motion. The relationship between gear sizes and rotation speeds involves ratios. Planetary gear systems, which are used in automatic transmissions and many other applications, have gears rotating around other gears. The kinematics of these systems requires trig to figure out speeds and torques. Electric motors work by electromagnetic forces between rotating parts. The torque varies sinusoidally as the rotor rotates. AC motors are powered by alternating current, which varies sinusoidally. The motor design needs to match the AC frequency for efficient operation. Understanding motor behavior requires analyzing the trigonometric relationships between current, magnetic field, and torque. Gyroscopes are fascinating devices that maintain their orientation as they spin. They're used in navigation systems, in smartphones for screen rotation, in drones and aircraft for stability. The physics of gyroscopes involves angular momentum and precession, and the math is heavy on vectors and rotations, lots of trig. Satellites in orbit are constantly falling toward Earth, but moving sideways fast enough that they miss. The orbital path is an ellipse, or a circle in the special case of a circular orbit. The satellite's position, velocity, and acceleration all vary sinusoidally in certain coordinate systems. Ground stations tracking satellites need to predict where the satellite will be at any time, requiring solving the equations of orbital mechanics. Even something as simple as a clock involves circular motion. The hands rotate at constant angular velocities. The hour hand completes a rotation every 12 hours, the minute hand every hour, the second hand every minute. If you plot the vertical position of the tip of the second hand over time, you get a sine wave. This is why sine curves are sometimes called sinusoidal waves, or simply sinusoids. They're the shape traced by projecting circular motion onto a line. Before we wrap up, I want to take a step back and think about what trigonometry tells us about mathematics and the universe. Trigonometry is about cycles and rotations. Circles, spirals, waves, oscillations. These patterns show up everywhere in nature. Planets orbit in ellipses. Light waves oscillate. Atoms vibrate. Populations cycle. The seasons repeat. Day and night cycle. Heartbeats pulse. The fact that all of these diverse phenomena can be described using the same mathematical functions, sine, cosine, exponentials, suggests something deep about the structure of reality. There's an underlying mathematical order to the universe, and trigonometry gives us a language to describe part of it. And the connections between different areas of math, between trigonometry and complex numbers, between trig and calculus, between trig and geometry, these connections hint at a deep unity in mathematics. Different branches of math aren't separate subjects. They're all part of one interconnected whole. Euler's formula is maybe the best example of this. It connects E, the base of natural logarithms, which comes from calculus and the study of growth. It connects I, the imaginary unit, which comes from algebra and the study of equations. It connects pi, which comes from geometry and the study of circles. And it connects them through trigonometry. 5 different areas of math meeting in one equation. There's something almost mystical about that. It suggests that mathematics isn't something we invented arbitrarily. We discovered it. It was there all along, woven into the fabric of reality. Trigonometry teaches us that the universe has patterns, that these patterns can be expressed mathematically, and that understanding these patterns gives us power to predict, create, and innovate. It's a lesson that applies far beyond any specific trig problem. So that's trigonometry. From ancient Egyptians calculating pyramid slopes 4,000 years ago to modern quantum computers manipulating qubits. From Greek astronomers measuring the cosmos to engineers designing self-driving cars. From Indian mathematicians introducing the sine function to Euler connecting it to complex exponentials. From Fourier's insight that any wave can be built from pure tones to the MP3 compression on your phone, the Greeks systematized it, creating the first trig tables and establishing it as a mathematical discipline. The Indians transformed it, introducing the sine function that we still use today. The Islamic scholars expanded it into a mature science with all 6 trig functions and sophisticated techniques. The Europeans integrated it with calculus and complex numbers, opening up entirely new applications. And in the modern era, trigonometry has become so embedded in technology that we barely notice it. Every time you use your phone, watch a video, listen to music, use GPS, play a game, take a photo, trigonometry is working behind the scenes. It's in the processors, in the algorithms, in the antennas, in the software. The future will bring even more applications. As quantum computers mature, they'll manipulate qubits through carefully designed rotations. As AI continues to advance, it will process signals, images, and patterns using techniques rooted in Fourier analysis. As we explore more of space, establish lunar bases, and perhaps send humans to Mars, we'll need even more precise navigation and orbital mechanics calculations. Virtual reality will become more immersive, requiring faster and more accurate rendering of 3D worlds. Augmented reality will overlay digital information on the physical world, requiring real-time tracking and spatial understanding. New scientific instruments will probe nature at smaller and larger scales. Climate models will get more sophisticated. Medical technology will continue advancing. All of this requires trig, and there will be applications we can't even imagine yet. Every major technological revolution has found new uses for old mathematical tools. The invention of the transistor led to computers, which led to the internet, which led to smartphones and social media and e-commerce. Nobody in 1950 could have predicted all that. Similarly, we can't predict what technologies will exist in 2050 or 2100, but whatever they are, they'll almost certainly use trigonometry. Because trigonometry is about waves, cycles, rotations, oscillations, patterns that seem to be woven into the fabric of reality itself. As long as we're trying to understand the universe, as long as we're building technologies that work with the physical world, we'll need trigonometry. So, to anyone who ever thought, when am I going to use this in real life? The answer is all the time, in ways you probably don't even realize. The GPS in your car, the compression in your music files, the graphics in your video games, the communication systems connecting your phone to the network, the medical scans that might one day save your life, all of it relies on trigonometry. And to anyone who finds math beautiful, who sees elegance in a well-crafted proof, who appreciates the deep connections between different areas of mathematics, trigonometry offers endless rewards. The way it connects geometry, algebra, calculus, and analysis. The way Euler's formula brings together the exponential, circular, and hyperbolic functions. The way Fourier's insight lets us decompose any signal into pure tones. These are among the most beautiful ideas in all of mathematics. So, whether you're a student struggling through homework, an engineer using Trig every day, a scientist pushing the boundaries of knowledge, or just someone curious about how the world works, trigonometry is your tool for understanding the rhythms and cycles that surround us. From the ancient pyramids to the farthest reaches of space, from the tiniest quantum particles to the largest galactic superclusters, from the notes of a symphony to the pixels on your screen, trigonometry helps us make sense of it all. And that 4,000-year journey from Egyptian architects to quantum computers, it's not over, it's still going. The next chapter is being written right now by researchers and students and engineers around the world who are finding new ways to apply these ancient ideas to modern problems. Maybe you'll be part of writing that next chapter. Maybe you'll discover a new application or optimize an algorithm or teach someone else about the beauty of trigonometry. Maybe you'll build something that relies on trig in a way nobody's thought of yet, because that's the thing about mathematics that endures. It never gets old. It never stops being useful. Every generation rediscovers it, reinterprets it, finds new applications for it. The sine and cosine that the Indian mathematicians described 1500 years ago are the same sine and cosine powering your smartphone today. And they'll still be there, still being useful centuries from now. That's the timeless beauty of trigonometry. It's ancient wisdom and cutting-edge technology all at once. It's simple enough to fit on a flashcard and deep enough to occupy a lifetime of study. It's everywhere and nowhere, invisible but essential, abstract yet concrete. So, the next time you see a sine wave, or calculate an angle, or notice something moving in a circle, take a moment to appreciate the mathematics behind it. Appreciate the thousands of years of human insight that went into understanding these patterns. Appreciate how this ancient knowledge powers the modern world, because trigonometry isn't just math. It's a testament to human curiosity, ingenuity, and our endless quest to understand the universe we inhabit, and that's something truly worth celebrating. Inverse trigonometric functions. We should talk about inverse trig functions because they're super useful and often confusing. Forward trig functions go from angles to ratios. Sine of 30 degrees equals 0.5. Inverse trig functions go the other way, from ratios to angles. If sine of some angle equals 0.5, what's the angle? Well, it's 30 degrees. We write this as arcsine of 0.5 equals 30 degrees, or sine inverse of 0.5 equals 30 degrees. The terminology can be confusing. Arcsine, arccos, and arctan are the inverse functions. Sometimes they're written as sin to the -1, cos to the -1, tan to the -1. But that -1 exponent doesn't mean reciprocal like it usually does in math. It means inverse function. So don't confuse sin to the -1 of x with 1 over sine x. They're completely different things. Now, here's where it gets tricky. Trig functions are periodic. Sine of 30 degrees equals 0.5, but sine of 150 degrees also equals 0.5. In fact, sine of 30 degrees plus any multiple of 360 degrees equals 0.5. So, if you ask what angle has a sine of 0.5, there are infinitely many answers. To deal with this, we restrict the range of inverse trig functions. Arcsine only gives you angles between -90 and +90 degrees. Arccosine gives you angles between 0 and 180 degrees. Arctangent gives you angles between -90 and +90 degrees. These are called the principal values. So arcsine of 0.5 is 30 degrees, not 150 degrees, even though sine of 150 also equals 0.5. You pick the angle in the restricted range. Inverse trig functions show up when you're solving equations. If you have an equation like sine of x equals 0.3, you solve it by taking the arcsine of both sides. X equals arcsine of 0.3, which is about 17.458 degrees. They also show up in calculus. The derivative of arcsine has a complicated form involving square roots. The integral of 1 over the square root of 1 minus x squared is arcsine of x. This kind of integral appears in all sorts of physical problems. In real-world applications, inverse trig functions are used whenever you need to find an angle from measurements. A surveyor measures the height of a building and the distance from the building. They want the angle of elevation. That's an inverse trig calculation, arctan of height over distance. We've talked a lot about sine and cosine, but let's give some love to tangent and the other trig functions. Tangent is the ratio of sine to cosine. Tan theta equals sine theta over cosine theta. It's also the ratio of the opposite side to the adjacent side in a right triangle. Geometrically, on the unit circle, if you draw a tangent line to the circle at the point 1, 0, and extend the radius at the angle theta until it hits that tangent line, the length of the tangent line segment is the tangent of theta. That's where the name comes from. Tangent has some interesting properties. Unlike sine and cosine, which are bounded between -1 and 1, tangent can take any value. As theta approaches 90 degrees, tangent approaches infinity. At exactly 90 degrees, tangent is undefined because you'd be dividing by cosine of 90, which is 0. Tangent is periodic with a period of 180 degrees, not 360 like sine and cosine. Tan of theta equals tan of theta plus 180. This is because sine and cosine both change sign when you add 180 degrees, so their ratio stays the same. The graph of tangent has vertical asymptotes every 90 degrees, plus any multiple of 180. Between these asymptotes, the function goes from negative infinity to positive infinity. Then there are the reciprocal functions. Cotangent is 1 over tangent, which equals cosine over sine. Secant is 1 over cosine. Cosecant is 1 over sine. These reciprocal functions might seem redundant. Why not just write 1 over tan instead of cot? But they come up often enough that it's convenient to have names for them. Secant, in particular, appears in calculus when you're integrating certain types of rational functions. In ancient and medieval mathematics, these functions were all considered equally important. Tables would list all 6 functions, but in modern practice, sine, cosine, and tangent are the main 3, and the others are used more rarely. Actually, there are even more trig-related functions that were used historically but are rarely seen today. Versine is 1 minus cosine. Haversine is half of versine. Execant is secant minus 1. These all had practical uses in navigation and astronomy when people were doing calculations by hand, and every little shortcut helped. But with modern calculators and computers, we don't need these shortcuts anymore. Let's talk about what sine and cosine look like as functions. If you plot sine of x as x varies from 0 to 360 degrees, you get this beautiful smooth wave. It starts at 0, goes up to 1 at 90 degrees, comes back down to 0 at 180, continues down to -1 at 270, and returns to 0 at 360. Then it just repeats forever in both directions. The shape is called a sinusoid or a sine wave. It's the shape of a pure musical tone, the shape of simple harmonic motion like a pendulum, the shape of AC voltage in electrical outlets. Cosine looks the same but shifted. Cosine starts at 1 when x is 0, goes down to 0 at 90, down to -1 at 180, back up to 0 at 270, and back to 1 at 360. It's the same wave as sine, just shifted to the left by 90 degrees. In math terms, cosine of x equals sine of x plus 90. The tangent graph is different. It's not a smooth wave. It has vertical asymptotes at 90 degrees, 270 degrees, and every one 80 degrees from there. Between each pair of asymptotes, it goes from negative infinity up to positive infinity. It's a periodic function, but it looks nothing like the gentle curves of sine and cosine. You can modify these basic functions. If you multiply by a constant, you change the amplitude, how high and low the wave goes. Sine of x oscillates between -1 and 1, but 3 times sine of x oscillates between -3 and 3. If you multiply the input by a constant, you change the frequency. Sine of 2x completes a full cycle twice as fast as regular sine. It has a period of 180 degrees instead of 360. If you add a constant to the input, you shift the graph left or right. This is called a phase shift. Sine of x plus 45 degrees is the same wave but shifted 45 degrees to the left. If you add a constant to the output, you shift the graph up or down. This is called a vertical shift. Sine of x plus 2 moves the whole wave up by 2 units. You can combine all these modifications. Something like 5 times sine of 2 times the quantity x plus 30 degrees plus 1. This is a sinusoid with amplitude 5, frequency doubled, phase shifted by 30 degrees, and vertically shifted up by 1. These transformed sinusoids can model all sorts of real-world phenomena. Let's talk about how people actually calculated trig values before computers and calculators existed, because creating those trig tables that everyone used for centuries was a massive undertaking. Remember Hipparchus and his chord tables? He had to calculate the chord length for every half degree from 0 to 180 degrees. That's 360 different values. And he did this by hand, using geometric constructions and clever mathematical tricks. One technique they used was called linear interpolation. If you know the values at 0 degrees and at 1 degree, you can estimate the value at 0.5 degrees by taking the average. This isn't exactly right because sine isn't a linear function, but it's close enough for small angles. Another technique was using angle addition formulas. If you know sine of 30 degrees and sine of 45 degrees, you can calculate sine of 75 degrees using the angle sum formula. You can build up a table of values by starting with a few known values and repeatedly applying formulas. Ptolemy improved on Hipparchus's methods. He developed more sophisticated techniques for calculating chord lengths with higher accuracy. His tables were good to something like 4 or 5 decimal places, which is impressive for hand calculations. When the Indians started using sine instead of chords, they developed their own calculation methods. Aryabhata created sine tables by dividing the 90-degree quadrant into 24 parts, giving values every 3.75 degrees. He used a technique involving second-order differences to improve accuracy. Later, Indian mathematicians like Brahmagupta and Bhaskara refined these methods further. Bhaskara in the 12th century gave formulas for calculating sine values with very good accuracy. The Islamic mathematicians took all this work and pushed it even further. They created tables with much finer divisions. Al-Kashi in the 15th century computed sine tables to incredible precision. We're talking 16 decimal places. This was done entirely by hand using clever algorithms. Al-Kashi's tables were the most accurate in the world at the time. When these tables reached Europe, they became crucial tools for navigation and astronomy. Sailors planning long voyages needed accurate trig tables to calculate their latitude and longitude. Astronomers predicting planetary positions needed them too. Creating these tables was serious work. It took years of calculation by teams of human computers. That's what they called people who did calculations professionally before electronic computers existed. The creation of logarithm tables by John Napier in the early 17th century made trig calculations easier because logarithms turn multiplication into addition, which is simpler. Actually, Pierre-Simon de Laplace, a French mathematician, said that the invention of logarithms, by shortening the labors, doubled the life of the astronomer. That's how big a deal it was. Now, let's talk about how trigonometry works in modern computing, because computers do trig calculations differently than we do by hand. When you learn trig in school, You probably used a calculator with sin, cos, tan buttons. You punch in an angle and out pops the answer. But how does the calculator actually compute it? The traditional method is using Taylor series. Remember those from calculus? A Taylor series expresses a function as an infinite sum of terms. For sine, the Taylor series around 0 is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. For small angles, just the first few terms give you a great approximation, but Taylor series can be slow to compute, especially for large angles, so computer chips often use other methods. One common technique is called CORDIC, Coordinate Rotation Digital Computer. It's an iterative algorithm that calculates trig functions using only addition, subtraction, bit shifts, and table lookups. No multiplication or division needed, which makes it fast in hardware. Another approach is to use lookup tables. Store pre-computed values for a bunch of angles in memory and interpolate between them when you need an angle that's not exactly in the table. Modern processors have huge caches, so this can be very fast. Graphics processing units, GPUs, are optimized for trig calculations because they do so many of them. Every time you move or rotate an object in a 3D scene, multiple trig operations happen. Modern GPUs have specialized hardware for this. They can do millions of sine and cosine calculations per second. There's also the fast Fourier transform, FFT. This is an algorithm that computes the Fourier transform super efficiently. Instead of needing n-squared operations for n data points, the FFT does it in n log n operations. This is a huge speedup for large data sets. The FFT is one of the most important algorithms in computing. It's used in signal processing, image processing, audio software, scientific computing, telecommunications, and it's about computing lots of sine and cosine values efficiently. We should talk more about spherical trigonometry because it's actually still super relevant today. Regular trigonometry deals with triangles on a flat surface. Spherical trigonometry deals with triangles drawn on the surface of a sphere. Why does this matter? Because the Earth is a sphere. Well, an oblate spheroid technically, but close enough to a sphere for most purposes. When you're navigating long distances on Earth, you can't treat it as flat. You need to account for the curvature. On a sphere, straight lines don't exist. The equivalent is a great circle, the largest possible circle you can draw on the sphere's surface. The equator is a great circle. Lines of longitude are great circles, but lines of latitude, except the equator, are not great circles. The shortest path between 2 points on a sphere follows a great circle. This is why airplane routes look curved when you plot them on a flat map. They're actually straight when you think about them on the sphere. Spherical trigonometry lets you calculate distances and directions on a sphere. The formulas are more complicated than regular trig because the geometry is different, but the principles are similar. You're relating sides and angles of triangles. The law of cosines for spherical triangles is different from the regular law of cosines. For sides A, B, C, opposite to angles A, B, C on a unit sphere, the spherical law of cosines says cosine of C equals cosine of A times cosine of B plus sine of A times sine of B times cosine of C.